Hi, in this video, we'll talk about a puzzle, a quantum mechanical puzzle. It's called Elitzur Vaidman bomb. So the situation is the following. We have a bomb and there is a possibility that the bomb may be faulty. So you want to have some sort of a detector which can detect whether the bomb is faulty without exploding the bomb. Now, classically, if you try to, let's say, detect such a thing, then either the bomb will explode or you will realize that the bomb is not working at all. So there won't be a possibility for you to sort of peek into the bomb and figure out whether the bomb is faulty or not. However, in the quantum mechanical case, it's possible to do that with high probability. And so let me describe the situation again. So you have a bomb. Okay, some sort of a bomb. And well, it may be faulty. So we have a doubt that it may be faulty. So you have placed a detector. And if the bomb is faulty, if you pass, let's say, something like a photon through the bomb, then the photon comes out as it is. However, if the bomb is working, then this bomb will explode. Now, there is a way to test whether the bomb is working or not without exploding it by placing this bomb into the Mach-Zehnder interferometer. So, as you've learned before, the interferometer has some mirrors and beam splitters. So this is a mirror, this is a beam splitter over here, and this is a source. And there are two mirrors. So mirror one, mirror two, and two beam splitters. So these are beams splitter one, beam splitter two, and these are mirror one and mirror two. And also there are detectors. So if I say that this is path 0, then a detector over here is there. So detector 0. And if this is path 1, then there is also a detector 1. Now recall that if a photon passes through this interferometer, then the probability of detecting at detector number 1 is 100%. Unlike the classical case where there is a 50% probability of getting detected at detector 0 and 50% at detector 1. Now, the idea is to place this device of ours in this interferometer. And if you do the calculation, you will realize that, well, if the bomb is not working, then again, it will be like the original case. So there will be a 100% probability of detecting at detector 1. However, if the bomb is working, even then there is a possibility of detecting at detector 0. So if the bomb is working, then 50% of the time, uh, the 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 device, the photon hits detector 1, and 50% of the time the photon hits detector 0. So the probability of getting detected at detector 0 is actually overall 1/4, right? So and this way you can sort of detect the bomb or detect whether the bomb is working on or not without blowing it up, right? So now let's try to put some equations in the picture. So we have a detector. So we have a detector, and Well, what happens is that if you pass, let's say, a quantum state within the detector, let me call it state B, then the detector measures in the 0, 1 basis. Well, firstly, if the bomb is faulty, then uh, we get the output, the same output, nothing happens. However, if the bomb works, then so this is if bomb is faulty, and if the bomb works, then the detector in the measures in the ket 0, ket 1 basis. And if a 0 result occurs, so if a 0 outcome occurs, then the 0 is returned. If a 1 outcome obtains, then the bomb explodes. And otherwise the okay. So this is sort of describing the situation that we talked about the interferometer, right? So now what we are going to do is that we'll use this sort of model of the detector to increase the probability of detection without exploding the bomb. So what we do is that we apply the rotation Ry of epsilon to, which is equal to cos epsilon minus sine epsilon and cos epsilon. So epsilon is a small number, epsilon very, very less than 1. Okay, and we apply it to the ket 0 vector. So our epsilon applied to the ket 0 vector will be cos epsilon ket 0 plus sine epsilon ket 1. Right. So this we will call our initial state. And well, if you pass this initial state, so one can look at two scenarios. Case one is if the bomb is faulty. So if I pass this state, let me call this state ket B. So case one, if bomb is faulty. Well, if the bomb is faulty, then if I pass through the detector, then I get back B, right? But we are going to apply the rotation before we pass it to the detector. So on every rotation, we get, so we are going to feed this state back to the detector and apply this Ry of epsilon, right? So initial state is B, then you pass to the detector, you get a state, I'll call that B prime, right? Which is the rotated state. Then B prime again gets fed back into the detector. So essentially we are applying the rotation repeatedly, right? And so if I look at this picture of a two-dimensional picture where the x-axis is the ket 0 and y-axis is the ket 1, then I get initially the state is ket B, which is, and this angle over here is epsilon. And then every time I pass it back into the detector, then it gets rotated by an angle epsilon, right? And so basically the system is driving it towards the ket 1 state. So if I do pi over 2 epsilon number of iterations, And then the angle that is rotated is pi over 2. And then if I measure the state, so at the end of the pi over 2 epsilon, the final state does so. So final state measure, so state, and you will get ket 1 with 100% probability, right? Because it would have rotated pi by an angle pi over 2, right? So that is the case where the bomb is faulty. So with 100% probability, um, in pi over 2 iterations, we get the state 1. Now, case 2 is bomb works. So when the bomb works, the detector actually measures in the ket 0, ket 1 basis. So let's take our y of epsilon ket 0, this state, initial state B, is equal to cos epsilon 0 plus sine epsilon 1, right? So what the detector does is that measures this state in the 0, 1 basis. So probability of bomb exploding in one sort of iteration is sine square epsilon, which is, if epsilon is small, this is nearly equal to epsilon square, right? And when it measures, it returns a ket 0 vector back. So in this case, we rotate the ket 0 vector, we get back to our original state B. So instead of rotating B again, we are just back to the original state ket B. And so in the next iteration, the probability of bomb exploding is again epsilon square. So in, let's say, pi over 2 epsilon iterations, so bomb exploding in pi over 2 epsilon pi over 2 epsilon iterations, by the union bound will be less than or equal to pi over 2 epsilon into epsilon square, which is equal to pi over 2 epsilon. Okay. So this is still very small because it's pi over 2 times. It can be made small by choosing our epsilon. So this is small, right? Now, what is the final state that we get? So the state is still remains ket B, right? And the ket B state is very close to the ket 0 state. So final state is over here, which is equal to cos epsilon ket 0 plus sine epsilon ket 1. So now when we measure, assuming that we haven't exploded the bomb, although there is a very small probability of the bomb exploding, but it can be made negligible, right? So assuming that we get back the final state, then if we measure, we'll get, so final state. So if I put the measurement on the final state, so input final state is ket B, and if I do a measurement on this, then we'll get ket 0 with probability cos square epsilon, which is nearly equal to 1, right? So what we have done is that if we get the final state and you measure a 1, then it's definitely the bomb is faulty. If we measure a 0, um, the bomb is definitely Okay, sorry. If I measure a 1, there is a small possibility of the bomb, you misreading whether the bomb is faulty or not. But if you measure a 0, then you are definitely saying that the bomb works, right? So in this case, the bomb works. There is a small probability of the bomb working and you still measuring a 1, but that's also very, very small. So this is called the Elitzur Vaidman bomb. And this is also one of those scenarios where quantum computing or quantum computers work, quantum mechanics works very, very differently than the classical case.